Good morning, good afternoon, and good evening, everyone, wherever you are, and welcome to the first Global Hydrogen Economy webinar for 2024. My name is Jiao Ma from ARC Training Center for the Global Hydrogen Economy and Particles and Catalysis Research Lab at UNSW Sydney. I'm a postdoc researcher in the center working on electrocatalysis, specifically into the electrochemical CO2 conversion into value-added chemicals together with NOx reduction for green ammonia synthesis. Before we start, I would like to acknowledge the Bidjigal people that are the traditional custodians of the land and that I'm presenting from today. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. Before we dive into the webinar, I would like to remind everyone to mute your microphone and also to post questions in the chat box if you have any questions. Please also note that this webinar will be recorded and uploaded onto the Global Hydrogen Economy YouTube channel. Today, I'm honored to be chairing the webinar where we will be hearing from our distinguished speaker, Professor Feng Jiao, on CO2 electrolysis systems for chemical and food production. Some of you may have known Professor Feng Jiao from his outstanding work, but just want to take a moment to introduce our speaker for today. Professor Feng Jiao is a full professor and also Averill and William R. Stackenberg Professor at Washington University in St. Louis. He completed his bachelor in chemistry from Fudan University in China and a PhD in chemistry from the University of St. Andrews in the United Kingdom. Following the completion of his postdoc training at the Lawrence Berkeley National Laboratory, he joined the faculty at the University of Delaware in 2010 and then was promoted to full professor in 2021 and served as the director of the Center for Catalytic Science and Technology. In August 2023, Professor Jiao joined the Department of Energy, Environmental, and Chemical Engineering at Washington University in St. Louis, and also serves as the director of the Center for Carbon Management. His research group develops innovative electrochemical devices to address critical energy and sustainability challenges. Professor Jiao has published over 100 research papers, which have collectively received more than 19,000 citations. His contributions have been recognized with several awards and honors, including his election as a Fellow of Royal Society of Chemistry, the receipt of NSF Carrier Award, and recognitions as a 2020 Emerging Investigator by the Journal of Materials Chemistry A and a 2020 Scienlog Fellow of the Negative Emission Science Initiative. In today's presentation, he will share his group's work on the development of a two-step tandem CO2 electrolysis system for acetate and ethylene production. So without further ado, let's welcome Professor Feng Jiao.
Thank you, Jiao, for very nice introduction. So first of all, let me put on my slides. Okay, hopefully everyone can see my slides correctly. So it's my honor to present our work here. We have spent the past decade or so working on CO2 electrolysis technology. Originally, we actually targeted for commodity chemical productions. Now we actually expanded to food production as well. So the kind of the central piece of my presentation today is going to share with you about acetate, one of the unique chemicals we actually can produce from CO2 using tandem process. So let me start with just one slide on the background. So this is sort of my vision of the future of chemical industry. I think right now the chemical industry is heavily relying on the fossil energy and the fossil source, and I think down the road we have to switch to more sustainable energy source and also produce our chemical in a sustainable way. So in my opinion, we will eventually utilize solar energy, directly or indirectly through renewable power generation. Then coupling with abundant sources, carbon can be sourced from CO2, and also we have abundant source of nitrogen, biomass, and water. Those can be as the input through electrolysis powered by renewable electricity. Then we can produce a range of fuels and chemicals we can utilize for our society. Today also, I'm going to touch a little bit on how to bridge chemical production, eventually tackle some of the challenges associated with food shortage and food security issues. So I want to start with give everyone a little bit of background about the technology we are working on, which is called the CO2 electrolyzer. CO2 electrolyzer is quite similar to the traditional water electrolysis system. Basically, we utilize two electrodes, cathode, anode. For cathode, we drive a reduction reaction, and for anode, we drive oxidation reaction. In between, we often use iron conductive membrane. In today's talk, I mostly focus on near ambient temperature operation. So we most of the time utilize a polymer membrane, either a cation conductive membrane like a naphthalene or anion exchange membrane like a sustainium. So on cathode, as I mentioned, we mostly trying to address the CO2 reduction reaction. For CO2 reduction, you actually can drive this particular reaction through multi-pathways, which means is starting with CO2, you actually can produce a wide range of products. This actually is a good thing, but also at the same time, it's also being challenged when you're trying to be selective. At the same time, if you conduct this reaction in aqueous electrolyte, oftentimes we run into is the competing reaction, hydrogen evolution reaction, and we try our best to suppress hydrogen evolution reaction and promote CO2 reduction reaction on cathode. On the anode side, most of the time, what we drive using the anode to drive is the oxygen evolution reaction. So oxygen actually is being produced as a byproduct. So the tandem system is one of the systems we introduced. We started this investigation probably back to 5 years ago. And the kind of the motivation for proposing this new tandem process is trying to address is the carbonate formation issue. So let me just give everyone a little bit of background about what is the carbonate formation issue. So back to more than 5 years ago, probably close to 10 years ago, when people drive CO2 reduction, and most of the time we conduct this type of research in a typical batch reactor. It's called an H cell. However, CO2 has very low solubility in aqueous electrolyte. So which means the limiting current you can drive this reaction is pretty limited. Usually you can go up to maybe 30 or 40 milliamp per square centimeter. Then later on, people introduced to the field is a gas diffusion electrode, so which allows CO2 being fast transported to the interface of the electrode and the electrolyte. And by doing so, you can operate the system in a flow system, and you can achieve a current density order of magnitude higher, which means you can easily get into hundreds of milliamp per square centimeter. Then later on, people find is using an alkaline electrolyte combined with the CO2 gas diffusion electrode, you actually can suppress hydrogen evolution. However, later on, it's about 5 years ago, people realized CO2 as an acetate gas, it will react with carbon dioxide, with the hydroxide and form carbonates. And the carbonates formation actually destroy the stability of the system. That's actually one of the challenges we are facing. So there are several promising technology actually being proposed for CO2 to CO production, for example, using solid oxide electrolysis systems or using bicarbonate-mediated electrolysis, or very recently, people started looking into bipolar membranes. And all of these can produce carbon monoxide pretty selectively, up to over 90% selectivity. However, some of those systems have certain limitations. It's really hard to produce multi-carbon products very selectively. So that's why we actually look into, can we develop a tandem process, take advantage of a new CO electrolyzer, and also take advantage of CC coupling actually is more favorable at a high CO pressure. We actually can promote the selectivity towards acetate and ethylene at a very high selectivity. Right now, we can achieve consistently over 80%. This is something I'm going to talk mostly for this talk. So I want to start to talk a little bit about the fundamental side of this interesting CO reduction system. So as I mentioned, people looking into this flow system using gas diffusion electrode. On the top left is one of the schematic we're showing. We call the 3-compartment microfluidic cell using a gas diffusion electrode as a cathode, copper as the catalyst, and also using KOH as a supporting electrolyte. We actually managed to achieve a current density close to 1 amp per square centimeter. The introduction of this gas diffusion electrode actually really facilitate a fast transport of gas reactant like CO2 or CO to the interface, and also drive the reaction current density much higher than traditional we can do. So one of very interesting phenomena we observe in this type of system is the formation of acetate. So one of the experiment, I think it's a very smart experiment actually, my student conducted about 6-7 years ago, is using the flow system, quickly switch the gas feed into the system. Okay, so let me go back one slide. Looking at the schematic on the top left, actually you can quickly switch the gas to the system. And because the cell is very small, the reactor is very small, the residue time for the gas reactant in the system is less than 1 minute. So within a minute, you can switch from one reactant to a different reactant. That allows us to study the catalytic behavior of the catalyst under different atmosphere. So this is one of the tests we, the left one we use the so-called oxide-derived copper. It's basically a high surface area copper catalyst. When you switch between the CO gas versus the CO2 gas, what we discovered is we still produce a significant amount of ethylene, a significant amount of ethanol, and also a little bit of propanol. However, under CO reduction conditions, we observe a higher selectivity of acetate compared to if you switch to carbon dioxide. And we repeated the gas switch several times, and we found that the phenomenon actually is pretty consistent. And also we compare to different catalysts, even under micron particle, copper particle, we still observe very significant amount of acetate formation. So this actually caused some kind of a puzzle at the time, because in the community, people are always talking about CO2 first need to be reduced to carbon monoxide, then through CC coupling, you form is multi-carbon product. So in principle, if you start with CO2 or CO, you should observe similar products. But in reality, we actually do see significant difference in acetate formation. So why? Why is that? So one thing we can think of is the major difference between CO2 and the CO is the CO2 actually is acidic gas. It will spontaneously react with hydroxide, while if you look at the carbon monoxide, it's inactive with carbon hydroxide. So we think because the side reaction between CO2 and the hydroxide may change the pH at the interface. So we did a simple modeling. Basically, you can see is that the dashed line represent carbon monoxide reduction, and the solid line represent carbon dioxide reduction at 3 different current densities. And in all cases, CO reduction have much higher pH at the interface compared to CO2 reduction. This is kind of easy to understand because the side reactions bring down the pH. So in other words, the hydroxide concentration at interface may link to the formation of acetate. Although how it's linked, we still don't have any clue. So one very interesting thing happened during when we're trying to publish our first paper on this topic is the reviewer asked us to explain what's the linkage between the hydroxide concentration at the interface versus the acetate formation. So I actually read this computational paper published by a group at UC Berkeley. They basically look into computational method, look into the reaction pathways. In the paper, they sort of talking about is the reaction mechanism they propose for acetate formation could be probed experimentally, although this is a computational paper, they didn't actually explain it. So basically they think is if you look at the source of oxygen, acetate has 2 oxygen in it. If you look at the source of oxygen, that may give you some hint about the reaction pathways or even disclose some of the information regarding the intermediates. So we actually did this experiment. We used oxygen-labeled carbon monoxide to do this CO reduction. What we found is only one of the oxygen in acetate is labeled, which means the other oxygen actually is not originally from the carbon monoxide you feed into the system. So in other words, that oxygen must come from the solvent and the electrolyte, either hydroxide from KOH or water or water-derived OH. So this is a very important piece of information that actually give us some hint is when 2 CO2 molecules coupling on the surface of a catalyst, they form this kind of 2 oxygen, 2 carbon intermediate. Somehow, one of the oxygen has to leave. Okay, so you form another intermediate, which has 2 carbon from CO, but 1 oxygen with only 1 oxygen from CO. The second oxygen actually comes back from the solvent or hydroxide derived from the solvent. So basically you have 1 oxygen from the solvent, the other oxygen from CO. So this is sort of give us some kind of idea how the acetate got formed. So we actually at time we propose this intermediate B is very likely is like a ketene type of intermediate. Basically you have a carbon-carbon double bond with a carbon-oxygen double bond. And the ketene is very reactive to water or hydroxide. You actually can form this acetate. So that's actually explain our observations on why hydroxide concentration at the interface enhance the formation of acetate. Now I want to switch a little bit on the topic, trying to talk a little bit more about how we can bridge these kind of fundamental studies, trying to understand the reaction mechanism and all the way to a device level work. So in my lab, we studying with catalyst fabrications and gas diffusion electrode fabrication, also single cell reactor engineering and design, and all the way to system integration. On the top right is the latest version of a multi-cell stack and connect 2 stacks connect in tandem to do this tandem CO2 electrolysis for acetate and ethylene production. So, okay, when you're trying to scaling up, we actually look into different cell designs. What we found is zero gap design. So-called zero gap design means is you put a 2 electrode right next to the membrane. You don't have any liquid electrolyte present between the 2 electrodes. Okay, that's so-called the zero gap design. The zero gap design is highly scalable because it's have been utilized in fuel cell communities and water electrolysis communities. And because you have a very short distance between the two electrodes, you actually can minimize the internal voltage loss, okay? So basically, you're trying to push the high efficiency of the energy, utilize the energy. And also, we actually take advantage of the anion exchange membrane we use, which allows anything carries negative charge can be easily crossed over. But also, any intermediates with no charge, non-charged species can also cross the anion exchange membrane if you choose a suitable anion exchange membrane material. So basically, in our design, we try to allow two things to cross over. One is acetate, the other one is ethanol. Okay, the only product cannot cross over is ethylene. And because ethylene is a gas product, and they will stay mostly on the cathode side, they have a hard time to diffusion through the porous media of AEM and to reach the other side. So on the anode side, what we actually trying to do is take advantage of the anode catalyst. Remember, anode drive oxidation reaction. The key reaction is oxygen evolution reaction. But at the same time, if you choose the right anode catalyst, you can also drive a reaction you want. For example, in our case, we actually put a nickel iron-based catalyst to drive partial oxidation of ethanol into acetate. So by doing so, we can collect exclusively high purity acetate product stream on the anode side. So this is the performance we achieved. So this is a piece of data we actually reported about 2 years ago. So we actually get over 100 hours continuous operation for CO reduction to acetate and ethylene. So acetate selectivity is about 50%, and ethylene selectivity is about 30% across the 100 hours operation. One thing I have to mention here is the acetate Friday efficiency actually is based on one assumption: all the acetate is produced from the catalytic reduction reaction. So we actually, for those ethanol partially oxidized back to acetate, we still consider this is a reduced product. So which means the total Friday efficiency will be slightly lower than 100% in our case, because some of the acetate may take more than the required electrons to produce. Okay. So, and this is one very first prototype we built in the lab for this tandem CO2 electrolysis system. It's at water scale, which corresponding to about 5 square centimeter electrode area. And this is operational pretty nicely. And here is the data for this first generation prototype with a 5 centimeter electrode size. So on the top panel, we have 2 lines. The red line represents the first electrolyzer, which is a CO2 electrolyzer. And the dark blue line represents the CO electrolyzer. So the blue dots represent the purity of acetate we can produce, which actually is close to 100% of purity, which means you don't have any other carbon-containing species in the liquid product stream out of this CO electrolyzer. And also across these 200 hours continuous operation, you can see the product distribution changes slightly. Most of the time, actually, you have a slightly higher hydrogen evolution reaction take off, starting from 10–15%. And after 200 hours, it's close to 30–35%. This is mostly because of could be potentially flooding issues of the GDE, which promote hydrogen evolution. At the same time, it could also be some of the anode, the metals leach out, may cross the membrane and reach the cathode. So you basically have a slow poison effect on the cathode catalyst. So very recently, we actually just submitted this work and going to be published very soon, is a scaling up effort from 5 square centimeter all the way to 1,000 square centimeter prototype. So just give you some numbers. So the total current we operate the system is at 300 amp, and we achieve about 95% of carbon selectivity. I have to explain the concept of carbon selectivity. Basically, is the converted carbon dioxide and the carbon needed end in ethylene or acetate. It's about 95% of those converted carbon dioxide carbon and in ethylene and acetate. And also, the cell voltage is about 2.4 volt operate at 300 milliamp per square centimeter, and the hydrogen finality efficiency is consistently lower than 20%. So, of course, scaling up is not easy task. There are so many challenges we actually trying to address. Some of them we addressed, some of them we haven't yet. So I want to give some kind of a list of problems we at least are aware of, and just share with everyone here. So if you work with larger cell and also multi-cell stack, sealing is always a big challenge. The leakage of gas and the liquid always pose a big challenge for the student and postdocs in my group. And we work with different gasket sealing mechanisms. We're trying to address it. So we're actually still struggling sometimes for the sealing. So mass transport, when you have a much larger system, the transport become even more challenging. How you deliver the reactant and also how you collect the product become the issue. And also quality control of electrode membrane at larger size. You kind of can imagine when the electrode become bigger and bigger, how uniformly you can coat the catalyst layer is actually pretty critical, because you don't want to create a hot zoom on your electrode. The hot zoom actually will generate a local high heat, and it will increase the temperature and bring down the membrane. So this is something we actually observed multiple times already. Temperature effect, whether you want to maintain the temperature and the ambient temperature, or you want to slightly increase it at larger system, cooling or heating actually is a significant effect. Selectivity and conversion trade-offs at the larger system, this is something we actually recently look into. What kind of selectivity we're trying to achieve, of course, as high as possible, but sometimes it's difficult to achieve a high selectivity at a high conversion. Stability for long-term operation, of course, this is a major challenge in the field. How we can go beyond, say, a few hundred hours without even at larger system. This is, I think, not many groups actually demonstrate that. Product separations and purifications are also a major challenge. And finally, everything comes down to the cost. So a few lessons we learned, and also I want to share with everyone a little bit what we actually have discovered is when you go from 1 square centimeter to 100 square centimeter, your gas diffusion electrode is much easier to be flooded. This is probably easy to be understandable, is you have a larger area for the water to come across. So you have to kind of introduce kind of a mechanism to block the water crossover. So one of the mechanisms we actually spend quite some time to look into is how to play with the hydrophobicity of the gas diffusion electrode. So what we discovered is to use we call the FEP layer coated on this micro porous layer, the GDL, and between the catalyst and the GDL, put this FEP layer actually help stop, not really completely stop the flooding, but slow down the flooding. And that's actually demonstrated by the data on the left. If you don't put any this supporting layer, your system actually, the hydrogen evolution take off within the very first 50 hours, you get to almost 50% Fe hydrogen. But if you put FeP there, you actually can maintain over 100 hours, the hydrogen Fe is still lower than 20%. So pretty significant improvement. The other one is I just mentioned the selectivity and the conversion trade-off. As I mentioned, we all want high selectivity and high conversion, but in reality, when you're trying to push the conversion, you lose the selectivity. So we actually look into the tech economics aspect of this trade-off and trying to identify what is the optimum operation condition for this tandem process. Temperature also play an important role. Heat management is particularly important for larger system. So when we doing small scale single cell test, we didn't actually notice any temperature variation. The cell may get a little bit hot, but barely higher than the ambient temperature. But when you go to 100 square centimeter and multi-cell stack, the temperature actually can go as high as over 100 degrees C. So the data on the left is just one simple demonstration. When you operate 100 square centimeter electrolyzer versus a 25 square centimeter electrolyzer, just single cell, you will see a significant increase of the temperature from about 33 degrees C to almost 50 degrees C, just within a few hours. Okay. If you don't do actively cooling, the temperature can go much higher and also eventually will destroy the membrane material. So this is what we end with this 1,000 square centimeter prototype. So we actually can operate the system at about kilowatt scale. And this is a tank of potassium acetate we produce. It's about, the purity is about 95%, and concentration is about somewhere between 1.2 to 1.7 mole. Cell potential we use is 2.4 volt and 300 milliamp per square centimeter. The production rate right now we can achieve is about 1 kilograms per day. And also we maintain a 40% acetate failure efficiency over 200 hours. And if you look at it closely, for huge tank of the potassium acetate we produce is close to 100 liters. And if you compare to the regular size of a gas cylinder, it's about the same tall, but much bigger. So, okay, I want to use my last maybe 10 minutes-ish to talk a little bit about how we can use CO2 electrolysis technology, for example, the tandem process, to go beyond commodity chemical production. Why we want to go beyond the commodity chemical production? First of all, is about the cost. Electricity price, at least in the United States, is still expensive. So in the same time, commodity chemical actually is relatively cheap. Okay. Second of all is the scale. If you look at the global citric acid market, it's about $9 billion. It's equivalent to 60 million tons per year. It's decent size, but it's not big enough compared to the CO2 emission, which currently is at 30 gigaton per year. Basically, it's off by 3 orders of magnitude. Okay, there's a clear mismatch in the scale. So that's why it motivated us to think about, can we produce something more valuable at a much larger scale from CO2? So we come with this formula, power plus CO2, and get into the food. So this may be a new opportunity, not only tackle the CO2 emission issue, but also trying to address the food shortage and security issue, particularly under global warming kind of environment, and traditional agriculture actually got threatened by this climate change. So nature does this CO2 fixation and group crops, and we can eat. So nature does this all the time, right? But there's one problem. It's not that efficient. So from the solar energy, to the biomass you can eat, the efficiency, the overall efficiency is only about 1%. So we want to create a pathway, go much higher efficient, and also use less resources. So this comes to our recent collaborations. The paper is published 2 years ago, but the collaboration actually started back to 2017, 2018, 17-ish. So it's a group at UC Riverside. So what we come with is if you have renewable electricity or some other electricity source, we could drive this tandem process converting carbon dioxide into acetate. Of course, this acetate could be used not just for chemical, but also to support food production. How that's even possible? Actually, we discovered is acetate is involved, is known actually in many metabolisms in biological systems like yeast, mushroom, algae, and plants. So if we feed acetate to those organisms, and maybe those organisms can utilize acetate as not only the energy source, but also the carbon source. And that will enable us to produce food product out of acetate, and that acetate can be derived from CO2. So Science actually published a very nice story about this kind of technology. If you read it, it's called Let There Be Dark. Basically, the concept is if this concept works, we actually could create a pathway to grow crops or food products without the involvement of sunlight. Okay, and this technology actually we have competed for NASA Deep Space Food Challenge right now, and we are in the final phase, and we're trying to grow as food products out of this technology. So, and I think there will be plenty of rooms to implement this kind of technology on Earth, particularly if you think about places the traditional agriculture is extremely difficult. For example, the middle of a desert, okay? Because this technology don't use traditional agriculture land. So it could be implemented in any land you can imagine. So what is the efficiency we can achieve? So as I said, the traditional agriculture utilize these photosynthesis pathways is only about 1%. If you calculate the demonstration we have done using this CO2 electrolysis tandem process to acetate, then acetate to grow algae, and this process actually is 4%. So 1% versus 4%, you may think, okay, this is not a big deal, but actually this is a 4 times difference. So put it more to a perspective. So if you think about the land resources we are using for agriculture, it's huge, okay? In the United States, there are about 1.2 billion acres land actually being used for agriculture, okay? If we can improve the efficiency, and this potentially can use much less land. For example, if we talking about, this is the name I created called the electroagriculture, basically coupling electrochemistry with agriculture for food production. We can actually use only 0.07 billion acres land. This is about the size of Missouri, which is University of St. Louis, Washington University in St. Louis actually located. This is the 94% of saving on the land, but also at the same time, this actually requires less resource. So I think this become more manageable, and particularly for some countries, which the agriculture is very, very difficult. So we actually, my team actually participated a consortium is called Acetate Consortium. The consortium is the aim of the consortium, the goal of the consortium is to utilize CO2 as a sustainable raw material, and eventually we can use it for food production. The target food product for this consortium is protein-based products. Using fermentation technology coupling with our electrolysis technology, we actually could potentially produce proteins out of CO2 and electricity. This is consumption just from last year. We actually raised $27 million for both from both the Novo Nordisk Foundation and the Bill Gates Foundation. We have partners mostly in Europe. Topsoe, Novozymes is a fermentation company. Topsoe is a solid oxide electrolysis company. We have a CO2 research center funded by Novo Nordisk Foundation, and also Washington University is my group, actually is also part of this consortium. So we are very close. Next month will be our annual review meetings for this consortium. So what are the challenges, opportunities? Okay, sometimes challenges are opportunities. So I want to share a little bit about what I learned over the past year. So when we focus on CO2 electrolysis, we're talking about fire efficiency, but at the end of the day, it's about the purity of the product, how pure you can produce it, and how much you need to pay for the separation. Purification and separation actually is pretty energy intense and cannot be ignored. And also, can we stably operate the system? Right now, we can operate the system for maybe 100 or 200 hours. The longest we can operate in my lab is close to 700 hours, but it's far from the commercial stability requirement, which is typically a few thousand hours. So, and also the efficiency. Not all the species we're looking to, particularly on the biological side, could utilize acetate very efficiently. So, which means, can we do some engineering on those species and let them take acetate more efficiently? And also the cost. When you're talking about commercial opportunities, it's all about the cost, whether this is cost effective compared to the existing process. This is another kind of challenge we have to address. Is acetic acid produced through electrolysis cheaper than the traditional acetic acid production process? And the last thing, also very important, is the food safety. When you're talking about the food, the first question, general public will respond is it safe to eat? So I want to share one story. When we first published that Nature Food paper 2 years ago, I got interviewed by BBC. The first question by the host is, "Oh, can you tell us is whatever you produce is safe to eat?" So I think public acceptance for those food products is something we have to work on. We have to ensure our technology actually is safe. Okay, so finally, I want to come down to the acknowledgement. My team collaborated and a funding source to support me. And I have very last slide. So yesterday in US, we just have a very beautiful event is solar eclipse. So this is one of the photos I took yesterday. It's about close to St. Louis. It's about a 1 hour drive from here. So thank you, everyone, and happy to answer any question you may have.
Thank you, Professor Jiao, for sharing your knowledge and your work with us, especially the challenges and tips in scaling the CO2 electrolyzer, CO electrolyzers, and also your concept study or the CO2 to food. And actually, from our audience side, you are welcome to provide your questions in the chat box if you have any. And before that, I have several questions from my side. And for your CO2 electrolyzer and CO electrolyzer, are these the same type of electrolyzer, or they are same? They are not in the same setup.
They are very similar, I would say. Of course, a different catalyst. The CO2 electrolyzer utilizes silver catalyst for cathode and the iridium-based catalyst for anode. And also you use very diluted potassium bicarbonate electrolyte. So it's about 50 millimole concentration. For the CO electrolyzer, we use a copper-based catalyst for cathode and a nickel-iron catalyst for the anode. And these are the major difference there, and also a very high concentration of KOH as supporting electrolyte.
Yeah, and as you mentioned, there's a zero gap electrolyzer for the CO electrolyzer. So
Yeah,
this
they
is
both
still
designed in that way. Yes.
Okay, they still have catalyte rather than like humidified CO or CO2 in that.
We trying to feed just vapors into it, but it didn't work out very well. Balance the water in the system actually is pretty challenging for CO2 electrolyzer.
Yeah, thank you. I can see one question from Rose. Rose mentioned, how do we solve the stability challenges? For example, any recommendation on what we need to do to achieve a few thousand hours of stability?
So I think there are several things personally our group actually working on, but I think the community should spend more time on it. Is first of all, we have to understand a little bit better on the fading mechanism. So one of the very well-known one is the flooding. I think the flooding mechanism is kind of known, particularly related to the GDE. But other than flooding, there are many other fading mechanisms. I think it's not fully understand at this moment. So I think some of the operando techniques need to be developed to really understand what's going on at the interface. So this is something we need to look into. Second of all, I think there are some fundamental challenge of this GDE system. I think, at least my opinion, completely address the flooding probably is a little bit over optimistic. I think maybe combining ways to slow down the flooding, but also at the same time develop a method to regenerate the interface. Combine these two, maybe we can get to 1,000 hours stability down the road.
Yeah, thank you, Professor Jiao. And following a flooding problem you mentioned, I think you mentioned you use a layer or FEP in your GDE preparation, and
Yeah.
normally we are using PTFE in our lab. So have you tried both of them? And
Oh yes, of course.
yeah.
We try several different options. I would say in some cases the PTFE. It really depends on what's the formula of the ink you use, and sometimes the PTFE works slightly better. Sometimes the FEP works slightly better.
Yeah, thank you. And we during our experiment, we found that there the trade-off of the conductivity when we try to increase the
Oh yes,
layer
of
of
course.
the yeah, thanks. And another question from Li Xue. When scaling up the electrolyzers, temperature goes up quickly. So can temperature affect the CO conversion or selectivity? And next one,
Yes,
yeah,
so that's a very interesting phenomenon. I think, generally speaking, there are not many publications on this topic, and based on the fuel cell community's work, of course, people trying to push the temperature higher, so you can gain some advantage of the fast kinetics. But in CO2 reduction or CO reduction, I think it's a little bit more complicated than that, because selectivity could also change at the same time. So based on our limited study and also some of the recent publication, we think maybe lower the temperature, reaction temperature probably is beneficial. So this is not a topic have been fully explored. So I think a very interesting topic to explore.
Yeah, thank you. I think you already answered Li Xue's second question. And the next question is from David Chen. Could you please elaborate more on the product separation? Is this issue specific to the CO2 acetate system, or it is more general challenge?
Okay. So I will say maybe 90% of paper, maybe 99% of paper don't report the conversion. I guess the conversion probably is less than 10%. So of course, in a realistic system, if your conversion is so low, you have to separate out your product from the unreacted feedstock, right? That's a huge cost. For liquid product, it's even worse because when you're using supporting electrolyte, the concentration could be very low. Distillation is really high energy intensive process and costs a lot. So, but I guess at this moment, the community didn't really talk too much about it. So it depends on what kind of a product you actually produce, and it's either liquid or gas, how you separate out, how you're dealing with this selectivity versus conversion. Also, there's one more thing, particularly unique to acetate and formate actually, is you produce is potassium or sodium or some kind of salt version of formate and acetate. But traditional industry usage of those chemicals actually is in acid form, not the salt form. So how you regenerate your QH feed into the system and take the ideal or the desirable product out. I think this is also something need to be worked out.
Yeah, thank you. And the next question from Johnny. Regarding the product gas separation and purification, could you please share your practice experience on gas separation and ethylene purification?
So at this moment, we don't do much of the ethylene separation. So for CO electrolysis, the separation, the kind of the gas effluent has hydrogen, unreacted CO, and ethylene, basically just the three of those. Trace amount of vapor of ethanol, that's less than 1%. So I think a membrane type of separator could work out, but some of the membrane don't like the vapor of the moisture. So actually, we are actively talking to those membrane separator groups and trying to figure out what's the most practical membrane materials out there we can use. So right now, the short answer is we just buy the commercial membrane separator, but it's not designed for CO reduction or CO2 reduction systems.
Yeah, thank you, Professor Jiao. And following your conversion topic, for your tandem system, so what is the CO2 conversion of your first CO2 electrolyzer, and would it affect the second CO electrolyzer performance as well?
So we try to push as high as possible. This is one of the issues, or maybe you could call it a smart designs, is the community knows that some of the CO2 will react and form carbonates are transported to the anode. So we actually take advantage of that. So the output of our gas product stream out of CO2 electrolyzer has over 95% of a conversion, but only half of them actually is converted to CO. The other half actually convert to carbonates. So we have to work out what's this going to affect the economics. But we do limit the separation cost for coupling with the CO reduction system. CO reduction system is pretty sensitive to any CO2 because it's running at a strong QH. Even you have a few percent of CO2 in the CO stream, it will slowly cooling the stability.
Yeah, thank you, Professor Jiao, and thank you all for your questions. Unfortunately, we are running out of time today, but we are grateful for your engagement and the participation in the webinar. If you have any further questions, please feel free to reach out to our speaker, Professor Jiao Feng, and through LinkedIn or contact us immediately. And as we bring this webinar close, we want to extend our sincerest appreciation to Professor Feng Jiao for sharing the invaluable insights and expertise with us today. And also, as shared in the screen, Please tune in our next webinar speaker on 30th of April with Dr. Yufei Jiao from UTS, who will share her research on novel electrocatalysis for highly efficient hydrogen production. The link to register is on the slide. Yeah. Thank you again for joining us, and have a wonderful day. Have a wonderful night, Professor Jiao.
Yeah, thank you. Thank you, everyone.
Thank you.
Bye.
Bye.